There is hardly anything more fascinating in a sci-fi movie than seeing the lasers blast off everything. But as fascinating as these beams of destructive light are, what actually are they and how are they made? You might have already figured out that laser beams are made up of light. But turning on a light bulb does not produce lasers, nor do flashlights, LED lamps, or any other light source you see every day. So what is so special about lasers, and why don't we see everyday bulbs and flashlights shooting lasers all around? To answer that, let's first see how light is produced in an incandescent bulb. The main light producing part in the bulb is the tungsten filament. When electricity passes through the filament, it gets really hot, and the electrons in the atoms of the metal gain energy from that heat and jump to a higher energy level. But electrons don't like staying in this unstable high energy for long. So they want to quickly jump back to the low energy state, which is sometimes also called the ground state. But to come back to the ground state, the electron must also release the energy it absorbed while jumping to the high energy state. So to release that energy, the electron emits a photon. A photon is a particle of light. It has no mass and it always travels at the speed of light. And the energy of a photon is determined by its wavelength. It might sound confusing to say that it's a particle and also has a wavelength, which is a property of waves. It is because matter has both the properties of waves and particles. But that topic deserves a whole video of its own. But the wave-like properties of matter are not so visible in everyday life because at the micro scale, the wavelengths of the things around us, like trees or the device on which you're watching this video, and even our own bodies, are so small compared to the size of the stuff around us that the wave-like behavior of the objects cannot be observed. But that is not the case with things that are at the scale of atoms and subatomic particles. Therefore, they behave both like waves and particles. And since photons are the particles of light, the wavelength of photons is the wavelength of light, and the more photons there are, the more intense the light is. So for now, just remember that the intensity of light tells us how much light there is, and the wavelength or the frequency tells us how energetic the light is. Lasers produce a very special kind of light. Unlike bulbs, which spread light in every direction, a laser beam only travels in one direction. Also, the light from a laser is coherent. Now what that means is it creates nearly monochromatic light, which is in phase. Monochromatic light is the light composed mainly of a single wavelength. And to understand what we mean by light which is in phase, let us look at these two different waves with the same wavelength and amplitude. These waves are periodic. This is to say that a single pattern keeps on repeating again and again, and the amount of time between each repetition is also known as the period of the wave. Also note that the frequency of the wave is the amount of repetitions completed in 1 second. Now because this wave is periodic, a particle moving along this wave can be thought of as moving along a circle, where let's say this point here corresponds to the peak of the wave and this point corresponds to the bottom of the wave. Now a particle moving along this circle will go down from the peak to the valley, then again from the valley to the peak, repeating this again and again. This is exactly the same thing that would happen if the particle was moving on the wave. Now the phase over here corresponds to location the particle currently is in its cycle, whether it just started out or is already halfway through. Let us bring back the other wave we had. What it means for two or more waves to be in phase is that they reach the same point on their cycle at the same time, matching their peaks to peaks and valleys to valleys. And if the waves are not in phase, the cycles do not match. So why is it important at all for the laser light to be in phase? Because of interference. You don't expect light waves to just ignore each other when they pass by, did you? So without going into too much detail, simply understand interference is when the crests and the troughs of the waves match up. The waves interact constructively and become stronger, and when they don't line up, the waves interfere destructively and they become weaker. So when the light from a laser is in phase, we can get a strong and intense beam of light. To recall, a laser beam is a narrow and intense beam of coherent light that travels in a single direction. So why care so much about light with these special properties? That you can't use lasers like a flashlight and you can't place them in place of bulbs. So where exactly are these lasers used? Short answer, everywhere. Long answer, it's too long to fit in a single video. But a few applications can be pointing at stuff, the barcode readers you see in stores, the optical discs you use to store your personal data, steel cutting, welding, measuring distances, precision surgery, the list just goes on and on and on. Ultra high energy lasers can even be used to achieve atomic fusion and create conditions in laboratories unachievable by conventional technology. So now that you know enough to go bragging about lasers to your friends, you might be wondering how are these lasers actually made. So do watch the next part of this video to learn more about that.